All right. I hope you all are doing well today. We're going to be talking about nodal analysis, which is a very powerful circuit analysis tool. It's fairly involved, so I'm going to save answering questions regarding prior homework assignments for the end of class today, so we can just kind of dive in and make sure that everybody understands what's going on. So we are going to approach this by looking at an easier case first and develop an algorithm or a process by which we can solve circuits using nodal analysis. And then once we get a good grasp on that, we'll add in some more difficult things. Okay. So this first nodal analysis that we're going to look at is with current sources only. And it does not particularly matter if we have independent or dependent current sources in. We'll take into account both. Okay. So we're going to learn nodal analysis by applying this technique to a circuit to kind of see what shakes out. So the circuit that we're going to analyze is as follows. We're going to have a short circuit here. Across the top, we're going to have a 15 ohm resistor. And here's some voltage Vx, positive polarity on the right. Across this branch, we are going to have a 5 ohm resistor. Let me make sure that 5 looks better. Here we are going to have a 20 ohm resistor. Here we will have a 10 ohm resistor. This will be a 2 amp source. And then over here on the right, we're going to have a voltage controlled current source like so. So this is the circuit that we are trying to analyze. And let's go ahead and define a few things that we are interested in ultimately solving for. So let's say that we want to know what the voltage Vx is. We also want to know the power supplied by the 2 amp source. And let's say we want to know the power supplied by our dependent source as well. So those are our 3 goals in solving this circuit. Okay. So our procedure from nodal analysis is going to be a step-by-step thing. And our first step is going to simply be to identify all of our nodes. And I'm going to do this just like I've done every other time I've identified nodes, by just using different colors and just kind of drawing the nodes out. So I'm going to have this red node on the top left. I'm going to have this blue node on the top right. I'm going to have a purple node here in the middle. And lastly, I'm going to put a green node down here on the bottom. Okay. So step 1 is literally just identify the different nodes. And so I feel like we've done that. Our second step is going to be to assign a reference or ground node. Okay. So we are just going to pick one of the nodes that we've identified, and we are using that node as a reference. So we are effectively saying the voltage at this node is 0, and all other voltages are going to be measured with respect to that ground or 0 node. So in a circuit like this, where there are no voltage sources, I am of the habit of placing my reference node at whichever node is connected to the largest number of elements. If we look at the red node, we can see that it's connected to 3 different elements. The blue node is connected to 3 elements. The purple node is connected to 3 elements. And the green node is connected to 3 elements. So all of the nodes are equally as good to serve as our reference node. So I would like you guys to just tell me which color our reference node should be.
Green.
Purple?
Oh.
So I heard one person say green and one person say purple. So selecting the reference node at any of them, like I said, is equally valid. The green node is a very obvious choice. It's at the bottom. And because it's the obvious choice, that's the reason I'm not going to do it. We're going to wind up getting the same results either way. So I'm going to choose the purple node as my reference. And I'm going to denote the reference node with a ground symbol like so, okay? So whichever node we choose to be our reference node, we need to indicate that on our schematic diagram. Typically, it's done by using a ground symbol. In some cases, you might see somebody literally just write REF for reference. All right, so our third step is to assign nodal voltages to all non-reference nodes. So what I mean by this very specifically is we're just going to effectively label each of our nodes with a voltage. And then those are the nodal voltages that we're going to wind up solving for using this analysis technique. So for example, I could say that the red node is node A, and so I'm going to assign a nodal voltage VA to that node. Similarly, the blue node will be node B, so I'm going to assign a nodal voltage VB to that node. And lastly, the green node will be node C, and so I'm going to assign a nodal voltage of VC to that particular node. Okay. So I want to explain what these nodal voltages are before we move along from this step. Okay. So a nodal voltage is just a shorthand notation for representing a voltage. It is effectively the same as the double subscript notation that I introduced you guys to on the second day of class, where the positive polarity terminal is at the node that's labeled, and the negative polarity terminal is always the ground or reference node. So I'm going to wind up erasing this in a second, but this nodal voltage VA is effectively the exact same voltage as the voltage drop across the 5 ohm resistance. The positive polarity terminal at our node of interest, and negative polarity terminal is at ground. VB, our nodal voltage VB, is the same thing as the voltage drop across the 20 ohm resistor, where the positive polarity terminal is at the node of interest and the negative polarity terminal is at ground. And lastly, VC could be thought of as simply the voltage drop across the 2 amp current source, where once again, the positive polarity terminal is at our node of interest and the negative polarity terminal is at ground. So hopefully you guys can all see that these nodal voltages are literally just a shorthand notation for expressing voltages, just like we've done at every other point in this class. Okay. So let me go ahead and erase these. So our fourth, and this is where we're going to start setting up equations, is going to be to express any controlling variables in terms of our nodal voltages. So this step only matters when we have dependent sources, because it's only when we have dependent sources that we have a controlling variable. So we have this dependent current source on the bottom right-hand corner of our circuit that has a value of 0.5 Vx. 0.5 is a scaling factor, the controlling variable. So this current source right here depends on this voltage Vx, which is defined as the voltage drop across the 15 ohm resistor. Okay. So our controlling variable relationship is going to look something like this. We're going to say that Vx is equal to, and now we need to see how these nodal voltages relate to this controlling variable. For voltages, it's actually pretty easy. So when we're going to write a voltage relationship like this, it's simply whichever nodal voltage is at the positive polarity terminal of the voltage we're trying to define, minus whatever nodal voltage is at the negative polarity terminal. So somebody tell me which nodal voltage is associated with the positive polarity terminal of voltage Vx.
VB.
VB, absolutely right. So the positive polarity terminal is at the blue node, and the nodal voltage associated with the blue node is VB. So VB is going to get a positive sign. Which nodal voltage is associated with the negative polarity terminal of our voltage Vx?
VA.
VA, absolutely right. So because it's on the negative polarity terminal, it gets a minus sign. Does not need to be any more difficult than that at all, okay? We don't have a controlling current in this particular circuit, but let's imagine that we did. So I'm going to define a current here. Let's call it IY. And let's see how we could express a current in terms of our nodal voltages, okay? So effectively what we're going to be using is Ohm's law, where we're going to have to figure out what the voltage drop across our element interest is in terms of our nodal voltages by the resistance, right? So since we're dividing by the resistance, it's fairly obvious that we're going to have something over 10 ohms. Now, defining the voltage drop across than we just did for Vx, but we need to be careful about the order of things because we want to make sure that the current, and we're describing the current that is flowing in the direction that's given. So how I like to think about this is whatever voltage is associated with the direction the current is flowing from gets a positive sign, and whatever nodal voltage that the current is flowing to gets the minus sign. So our current is starting from node A and it's ending at node C. So this should look like VA minus VC. Before we move along from this step, does anybody have any questions about expressing voltages or currents in terms of nodal voltages? All right,
So
so we're going to be doing this a whole hour. Go for it.
so these are just using Kirchhoff's voltage law and Ohm's law for the definition of Vx here.
That cut out or yours, but I heard so and then a very long blank space, and then I caught the tail end of a comment.
I'm sorry. I was just wondering, we're using KVL for defining our Vx here with VB minus VA.
Sorry, I think my internet is cutting out again. I heard something at the end that was just VB minus VA.
I think you are cutting out Dr. Hartman.
Sorry, I don't know why the internet here in Neskin Hall is so weird today. Could you repeat your question one more time? I'm so sorry.
It's okay. I was just wondering if we were using KVL for that first point where we defined Vx. So it's just VB minus VA is Vx because otherwise they would be zero.
So that is definitely a good way to think about things. So if I went back and I wrote this voltage as VA and this voltage as VB, if we were to do Kirchhoff's voltage law around this loop, just choosing this particular direction arbitrarily, we would have something that looks like negative VB plus Vx plus VA is equal to 0, and therefore Vx is simply VB minus VA. So that is what we are doing. It's just a shorthand way of doing that by saying whatever node is at the positive polarity terminal minus whatever node is at the negative polarity terminal.
Gotcha, that makes a lot more sense.
And the exact same thing for defining the voltage drop across our resistor of interest. Effectively, anytime we're doing a voltage, we are shorthand notating the voltage drop across any element of interest by just using that nodal voltage relationship. But that's really just a quick and lazy way of knocking out KVL around a particular loop. So, all right. So let's talk about step number 5 here. Okay. So we've expressed our controlling variables in terms of our nodal voltages. And so now what we're going to do is we are going to write a Kirchhoff's current law, or KCL expression, at each non-reference node. Okay. So we have 3 non-reference nodes for this particular circuit: node A, node B, and node C. So let's start with KCL at node A. And explicitly here, I'm going to be doing KCL where the sum of the currents that are exiting our node of interest add together to make 0. And I'll talk about why I do that specific thing with nodal analysis here in just a second. So if we're looking at node A, we should be adding these 3 currents together, right? So we're going to have one current flowing up, one current flowing to the right, one current flowing down. Add those 3 together and set them equal to 0. So let's start by defining the current that's flowing up in terms of our nodal voltages. Would anyone care to take a stab at that? All right, you guys are a little hesitant. That's okay. Effectively, we're going to do the exact same thing we did when we defined that current IY. So our current that we're interested in, it's this one flowing up through the 15 ohm resistor, is starting at node A. So I'm going to have a VA. It's ending at node B. So minus VB, and it's flowing through the 15 ohm resistor. So I'm going to have over 15 ohms. So this is the current that's flowing up. So if somebody doesn't mind, could they do that exact same process and tell me what the current flowing to the right through the 5 ohm resistor is?
Would it be a VA and then minus 0 because it's flowing into our ground?
So that's the voltage. What's next?
Uh, over 5 ohms.
Exactly right, Baylor. Thank you. So VA minus 0 over 5 ohms. And we put that 0 there because our ground is our reference node, which we are assuming to be 0. Okay. Somebody else tell me what the current flowing down through the 10 ohm resistor is going to be expressed in terms of our nodal voltages.
So the VA minus VC over 10 ohms.
So VA minus VC over 10 ohms, the exact same thing as we got for IY because they represent literally the exact same current. Absolutely correct. So there's our KCL expression at node A. Before we move along to our next node, does anybody have any questions about where those terms came from? All right. So now let's look at KCL at node B. So KCL at node B, let's see, that's the blue node. I'm going to have this current flowing up, this current flowing to the left, and this current flowing down. So let's start with the current flowing up. Could somebody tell me what the current flowing up and through the 15 ohm resistor is going to look like?
VB minus VA over 15 ohms.
Exactly correct. Now let's do the current flowing to the left through the 20 ohm resistor. Somebody else tell me what that's going to look like.
VB over 20 ohms.
Exactly correct. So VB, I'm going to put explicitly here minus 0, but you could just as easily leave this out, divided by 20 ohms. And then lastly, we've got something a little new here. I have the current flowing down through that current source. So how do you think we're going to approach that? So the short answer is that we're applying Kirchhoff's current law, which means we're just adding currents together. We are told that there's 0.5 Vx amount of current flowing down through that branch. So we're simply just going to add 0.5 Vx, right? So whenever we have a current source, this actually makes things easier. We don't have to do any circuit analysis whatsoever, really. We just take the information that we're told. So we had 3 paths leaving node B. We have 3 different terms here, so we're good. By the way, I hope it's obvious now why I'm choosing to use the Kirchhoff's current law expression where all of the currents exiting a node are positive, but if it's not obvious, I choose this particular method to do nodal analysis so that all of the VA terms in my KCL at node A are positive. All of the VB terms in my KCL at node B are positive, and so on and so forth. So it's just eliminating a bunch of extra negative signs that aren't going to do anything but confuse people. Okay. So let's do KCL at node C. I'm going to identify our currents, and then I want you guys to tell me what's what. So I'm going to have a current flowing to the left through my 10 ohm resistor, a current flowing up through that current source, and then a current flowing to the right through that other current source. So somebody tell me what the current flowing to the left through the 10 ohm resistor should be.
Just do a negative RY, which would be VC minus VA over 10 ohms.
Yep, so VC minus VA over 10 ohms. Absolutely correct. What about the current flowing up through the independent current source?
Two amps.
2 amps, absolutely right. And lastly, the current flowing to the right and up through the dependent current source.
Negative 0.5 VX.
So negative 0.5 Vx, because the current that we're interested in is flowing in the opposite direction of the current source. And we can tell that because the arrows are pointing against each other as opposed in the same direction. Great job. So negative 0.5 Vx. So let's count some things here really quickly. Okay, so we have this equation for Vx. I'm going to call this equation 1. We have this equation for KCL at node A. That's equation 2. This equation for KCL at node 3, or excuse me, node B, which is equation 3. And lastly, this fourth equation for KCL at node C. So we have 4 equations and we have 4 total unknown quantities, VA, VB, VC, and VX. So this is enough for us to set up a system of equations. Now, I have a caveat here, and I don't know if I did my normal calculator rant on the first day of class or whatever, but the calculators that you're allowed to use for this class, only the Casio 991 that was discontinued is capable of solving a system containing 4 equations and 4 unknowns. The Casio FX115, the TI-36X, and as far as I know, the HP33S are only capable of solving a system of equations that contain 3 unknowns. So because I'm not requiring anybody to get a specific calculator, we're going to talk about how we can reduce this down to a 3 equation, 3 unknown system. And it's really just simple substitution. So we could take this controlling variable equation, Vx is equal to Vb minus Va, and we could just substitute that anywhere we see Vx. And now we have 3 equations with only the unknown quantities Va, Vb, and Vc. So because I'm not physically with you guys and can't really teach you explicitly how to use your calculators, I'm going to talk my way through how I put things in mind. So what we're going to do is we're going to right now just kind of organize these equations, and you'll get to a point where you just do this kind of as part of the process. You don't actually write anything down. So if we look at equation 2, what I'm going to do is I'm going to take all of my VA terms and I'm going to lump them together. So I have a VA multiplied by a factor of 1 over 15 ohms from this part right here. Then I have a factor of 1 over 5 ohms from this part right here. And then I have a factor of 1 over 10 ohms from this guy right here. Is everybody okay with that? Nobody's saying they aren't, so I'm going to guess that you guys are all good. Then I'm going to pull out VB. So for VB, I only have this guy right here, so I'm just going to pull out a factor of negative 1 over 15 ohms. For VC, I just have this guy over here. So I'm going to have a factor of negative 1 over 10 ohms. And I don't have any constant terms, so I'm just going to set this equal to 0. So this would be how my organized or rearranged equation 2 is going to look. We're going to do something similar here for equation 3. So I'm going to pull out my VAs first. So I should have a factor of negative 1 over 15 ohms from this guy right here. And I will also have a factor of negative 0.5 from this guy right here, right? So 0.5 Vx is going to look like 0.5 VB minus 0.5 VA. So that's where that one came from. Now we're going to pull out our VBs. So that's going to look like positive 1 over 15 plus positive 1 over 20 plus positive 0.5. Pull out our VCs. Because there are no VCs, this coefficient is 0. And we still don't have any constant terms, so we're going to set this one equal to 0. And then lastly, we're going to work on equation 4. So I've got my VA here. I'm going to have a factor of negative 1/10. Oh, I'm sorry, I missed one. Minus negative 0.5, so that's going to look like plus 0.5. So that's from this part and this part. Just a moment. I'm in class. For VB, we are going to have a factor of negative 0.5. That's the only thing. For VC, we are going to have a factor of 1/10 or 1 over 10 ohms. And lastly, I'm going to move this constant term of 2 amps to the other side of the equal sign. So that's going to look like minus 2 amps. So I've written these expressions out in this way because these are telling us effectively what the coefficients we're going to put in our calculator are. I'm trying to think if there's a way I can show what I'm doing with my TI calculator. Let me see if I can sort that out really quickly. So let's turn video on. And I don't know how well you guys can see my calculator. Maybe if I don't screen share for a moment, this will be helpful for you. Let me stop the sharing. Does my calculator look any bigger?
Sir.
I could not hear. All I heard was sir. I couldn't tell if that was a no, sir, or a yes, sir. Sorry.
Oh, yes, sir. Yes.
Okay, it looks bigger. Great. So let me clear all this crap out. So for this TI calculator, our system solver is found by pressing second and then the tangent button, and it literally says system solver up above that in blue. So now I have this menu. Showing up as a very small thing on my screen, so hopefully this isn't too confusing. And we are asked whether we want to solve a 2x2 system or a 3x3 system. So we're going to be solving a 3x3 system in this case. I'm just going to go down to option 2, and press enter, and it brings up this thing that looks kind of like a matrix. It's got some information stored in there that I'm going to need to clear out real quickly. So let me go ahead and do that. Clear variables, and just for the sake of argument, let me go ahead and just reset the memory totally. All right, so now everything is showing zeros. So all I'm going to do is just type in those coefficients. So for the first coefficient, I'm just going to put in what I have next to the VA. So that's 1/15 plus 1/5 plus 1/10. So 1/15 plus 1/5 plus 1/10. And then I'm just going to press enter. And I'm going to let my calculator do the work for me. And it tells me that it's 11 over something that's too large for it to put there. And I don't really care. As long as I typed it in correctly, then the calculator is doing what it's supposed to do. For the next thing, I'm going to have the coefficient for VB in that first equation, which is just -1/15. Then I'm going to have the coefficient for VC, which is -1/10. And my constant term is 0. So this is what we should have if you're following along with a TI 36. So now I'm going to go to my second equation, and I'm just going to do the exact same thing over. I'm going to put my coefficient for VA in, then my coefficient for VB, then my coefficient for VC, and then my constant term. And I'm going to do the exact same thing for the rearranged equation 4 as well. So let me just run through that really quickly. So my coefficient for VA in my second equation is -1/15 minus 0.5. My coefficient for VB is +1/15 plus 1/20 plus 0.5. My coefficient for VC is 0. My constant term is 0. In my final equation, my coefficient for VA is -1/10 plus 0.5. My coefficient for VB is -0.5. My coefficient for VC is 1/10. And my constant term is -2 amps. So hopefully you all can see it, but this is what I have in my calculator after typing all of that kind of stuff in. So now if I press the enter button at the bottom here, it will spend some time thinking about things and solve it pretty quickly. I got X, which in this case is VA, to be -740/91. Y, which is the variable VB, -680/91. And lastly, VC or Z is -2260/91. The process is incredibly similar for those of you that have Casio calculators. So I just want to grab one of those off my desk real quick to show you. I'm not going to go through all of the steps. I just want to show you where the equation solver is so that you're aware of it. So here's my trusty Casio 115. To get to the equation solver for this particular calculator, I press the mode button. And then if you can see there, option 5 should say equation. So I press option 5 and it asks me effectively, option 1 is for solving a 2 equation, 2 unknown system. Option 2 is for solving a 3 equation, 3 unknown system. Option 4 is for solving a quadratic equation. Excuse me, option 3 is for solving a quadratic equation. Option 4 is for solving a cubic equation. So we would obviously choose option 2. Crap. And then the interface looks incredibly similar. We have places to put all of our coefficients in. And if we press over enough, we can see that the D column is where we would put our constant values. So you guys take a moment to play around with your calculator, and I'm going to write down the answers that I got, and hopefully you guys are able to get the same things. And if you didn't, then perhaps I made a mistake, which is always a possibility.
So I got the same answers you did, just positive instead of negative.
So did you put -2 or +2 as your constant term on that last equation?
Oh, I just put 2. That's why.
Yep.
All right.
That's an easy troubleshoot. Let me go back to sharing my screen. See what's popping off in chat here. I was not aware that Casio and TI have emulators for their calculators. That would be great. I will need to look into that. Thank you for that comment, Haley. So when I solved this system of equations, I got VA to be -740 over 91 volts, which is the same thing as -8.1318. So let's call it 132 volts. VB was -680 over 91 volts. And that's the same thing as -7.473. And lastly, VC was -2,260 over 91 volts, or -24.835 volts. So hopefully you all that were following along with your calculators got the same numbers that I did. I feel a little better now that somebody confirmed they got effectively the same thing as me. Chose a different round. But anyway, so let's assume then that these values are correct. If we look back at what we were actually trying to solve for, it's none of those nodal voltages, but we can use those nodal voltages to solve for every single one of these quantities, right? So this voltage Vx we found earlier is nothing more than VB minus VA. So using the nodal voltages we solve for, that comes out to be a voltage of 60 over 91 volts, or 0.659 volts. To calculate the power supplied by our 2 amp source, we need to know the voltage drop across the 2 amp source, as well as the current flowing through the 2 amp source. So I'm going to call this voltage V 2 amps, like so. And I chose the negative polarity on bottom so that the current would be flowing into the negative polarity terminal, so that whatever that voltage is times 2 amps is the current that's supplied. So how would we express that voltage V2A in terms of our nodal voltages?
Could you repeat that?
How do we express the voltage V2A in terms of our nodal voltages? So another way to think about this would be, what is the nodal voltage at the positive polarity terminal of V2A?
Would it be the voltage difference between VC and the ground, which is just VC?
So it's not going to be VC, it'll be negative VC, because we're
It's
going to
going
have,
into the negative.
yep, so 0 is at, the positive polarity terminal is at ground, so that's 0. The negative polarity terminal is at VC. So we'll have negative VC times 2 amps. So negative Z times 2 gives me 4,520 over 91, or 49.670 watts. For our dependent source, we can do something similar. So we want the power supplied by our dependent source. So I'm going to write a voltage V dependent, negative polarity on top, so that the current is flowing into the negative polarity terminal. So how am I going to express V dependent in terms of our nodal voltages?
Would be negative VB times 0.5 VX.
So I definitely agree that there's going to be a negative VB, and I definitely agree that there's going to be a 0.5 VX, which is just VB minus VA. But you're missing something. So whenever we're expressing a voltage, it's whatever node is associated with the positive polarity terminal, which in this case is VC, minus whichever node is associated with the negative polarity terminal, which in this case is VB. So if it were just negative VB, for what it's worth, that would be representing this voltage, where the positive polarity terminal was at ground and the negative polarity terminal was at node B. So let me throw that into my calculator really quickly. So Z minus I got negative 5.724 watts. All right, so there may be a couple of questions that you guys have on this one. I'm happy to answer them, but I think our time would be better spent working a practice problem here. So I want us to work ICA problem 1 really quickly. Let me pull it up. So, oops. For ICA number 1, we are given the following circuit. Okay. So we have a 10 amp source here on the left-hand side. We have an 8 ohm resistor in parallel with that 10 amp source. We have a 3 ohm resistor up top here. We've got a 4 ohm resistor. And a 2 amp source, like so. And we are already explicitly told that our bottommost node is our reference node. And we are told that there is a nodal voltage of V1 at this node on the top left and a nodal voltage of V2 on the top right. So effectively the problem was kind of set up for you, and you really just need to apply the KCL relationship part. So I'm going to go ahead and just kind of color everything in like we've done previously. So for this particular problem, you all were asked to determine the nodal voltage V1, the nodal voltage V2, and lastly, the current I, which is defined to be the current flowing from left to right through that 3 ohm resistor. So I would like for you guys to tell me what my KCL at node 1 equation is going to look like. So I'm not hearing anything. So
-10A.
okay, so negative 10 amps. So that's the term for the current that's flowing to the left. Thank you for that. Absolutely correct.
V1/8.
V1 over 8 ohms. Also absolutely correct. Thank you.
V1 minus V2/3 ohms.
Great job. That is perfect. Somebody else tell me what's going on at our KCL at node 2.
For the left, it'd be V2 minus V1/3 ohm, and then V2 plus V2 divided by 4 ohm
So just
And
V2 over
then-
4 ohms. Okay.
minus 2 amps.
All right. So we have 2 equations and we have 2 unknown quantities, so we should be able to solve these guys. Obviously, the answers are right there on the in-class assignment sheet, but I would appreciate it if you got practice using your calculator to solve this system. So I'm going to go ahead and resolve it. In my first equation, My coefficient for V1 is going to be 1/8 plus 1/3. And my coefficient for V2 is going to be -1/3. My constant term will be +10 once I move that -10 amps over to the other side of the equal sign. In my second equation, my coefficient for V1 is -1/3. My coefficient for V2 is +1/3 plus +1/4. And my constant term will be +2. When I solve this system, I get V1 is equal to 208/5 volts, and V2 is equal to 136/5 volts. And if I press the button that converts those into decimal numbers, I get 41.6 volts and 27.2 volts, which agrees exactly with what the answers are on the in-class assignment sheet. How do I solve for that current I now that I know what those nodal voltages are?
It'll be the V1 minus V2 over the 3 ohms.
Exactly right. V1 over 3 ohms. Which comes out to be 24/5 amps or 4.8 amps. Any questions regarding nodal analysis when we only have current sources? All right, so let's break things by including a voltage source. Oops. So I'm going to make up a problem here. So let's say that I have actually. So let's say that I have something like this. So let's put a 10 ohm resistor here. An 8 ohm resistor here. I'm going to put a voltage source over the top like so. Let's make this 2 Vx. Let's put a 6 ohm resistor here. Let's make this a 3 amp source. Let's make this a 5 volt source. And let's make this a 4 ohm resistor. So we now have a circuit that contains both voltage and current sources, and we are going to see that voltage sources are actually going to mess up our analysis process a little bit, but it's actually going to be slightly for the better. At least that's how I think about it, okay? So our steps are going to be very similar at the beginning. Oh, and I guess I need to define a voltage Vx. So let's define that voltage Vx to be this voltage right here across our 6 ohm resistor. Okay. So our first step is still going to be identify our nodes. So we've got this red node on the top left. We've got this blue node on the top right. We'll put a green node here on the bottom left. A purple node here in the bottom middle. And then lastly, an orange node on the bottom right, like so. Our second step will continue to be to assign a ground or reference node. So whenever we have voltage sources, I believe that it is best practice to choose a node that is connected to the most number of voltage sources. Well, in this case, the red node touches exactly one voltage source, the blue node touches exactly one voltage source, the green node touches exactly one voltage source, and the purple node touches exactly one voltage source. So all of those nodes are equally good to be our reference node. I tend to choose my reference node as one that is touching the negative polarity terminal of a voltage source for reasons that will become obvious here in a couple of minutes. So would you guys prefer to have the blue node or the purple node as our reference?
Purple.
Purple, okay. So we're putting our reference node down there. Step 3 is going to be assign nodal voltages to all non-reference nodes. So I'm going to call this one VA, this one VB, this one VC, and this one VD. Step 4 is going to be the exact same as we had before. So express our controlling variables in terms of our nodal voltages. So our controlling variable in this case is Vx, the voltage drop across that 6 ohm resistor. Somebody please tell me what our relationship is going to be.
Vx equals VB over 6 ohm.
So VB over 6 ohms is a current. Is a very, very common mistake there. So whenever I have a voltage divided by a resistance, that's a
So
current.
is it just without the 6 ohms, just VB minus the ground source?
Exactly right. So Vx is just equal to VB minus 0 or just VB. Okay. So there's going to be a step 5, but we are going to skip it intentionally. Okay. So instead, there's going to be a step 6, which I guess we're also going to kind of skip intentionally. I just want to show you where this breaks, and then we're going to fill these things in. So let's go ahead and just break things. So if we were to apply Kirchhoff's current law at node A, right? So that's this current up here. We would be adding this current plus this current plus this current together. So the current flowing down through the 10 ohm resistor is just going to be VA minus VC over 10 ohms. That's pretty easy. The current flowing down through the 8 ohm resistor is just going to be VA over 8 ohms. And then the current flowing to the right through the dependent voltage source, I was going to say a bit harder, but it is much more than a bit harder. It is literally impossible for us to express that current in terms of our nodal voltages. Because we have a voltage source, we know that the voltage that's being supplied by that source is fixed, and the amount of current that's flowing through it is just whatever current is required to make Telegen's theorem be satisfied, okay? So for a lack of a better term, I'm going to call this current I-dependent L comma R. So that's just the current flowing through the dependent source from left to right. I can't really do anything better than that for right now. So I've accidentally introduced a new variable into our system. Now, if we were to do KCL at node B, we would run into a very similar problem. So we would have this current flowing to the left through the dependent source, this current flowing down through the 6 ohm resistor, and then this current flowing down through the 3 amp source. So I'm going to call this current flowing to the left, kind of running out of room here, I dependent from right to left. Plus the current flowing down through the 6 ohm resistor, which is just VB over 6. Plus the current flowing down through our 3 amp current source, which is just 3 amps. So
Could I dependent be negative right now, or does it not matter since it's dependent?
So I have I dependent flowing from left to right in the first equation and I dependent flowing from right to left in the second equation, but you have definitely caught on to something there, Baylor. So those two currents, I dependent left to right and I dependent right to left, represent the exact same current flowing in opposite directions. So we could really treat them as a single variable. One of them would get a plus sign, one of them would get a minus sign. So what I'm going to do to fix this is going to seem a little bit weird, but this is the proper technique. I'm going to add those KCL equations together. So if I were to add these KCL equations together, I would have VA minus VC over 10 ohms plus VA over 8 ohms plus VB over 6 ohms plus 3 amps is equal to 0, where this current right here exactly cancels out this current right here because they represent the exact same currents just flowing in opposite directions. Okay. So this eliminates that variable that we've introduced that we literally have no way to express in terms of our nodal voltages at this point. So what I'm doing here is I'm treating, let me erase these, the combination of nodes A and B as what's commonly referred to as a supernode. Okay? So a supernode is going to happen whenever we have a voltage source. So literally for any voltage source in our circuit, we are going to have a supernode that just kind of ties together the two nodes that the voltage source is in between. So we have a supernode between nodes A and B, and we also have a supernode between nodes C and ground. So just to reiterate here, anytime we have a voltage source, there's a supernode that's kind of surrounding it. So our step 6 is going to be write a KCL equation for all supernodes which do not, and I'm going to underline that, contain the reference node. Let me erase all of this stuff over here. So instead of adding those KCL equations together, what we would do instead is we would just add up all of the currents that are leaving our supernode. So it would be this current right here, plus this current right here, plus this current right here, plus this current right here, which is literally just this result. I'll give myself a little room because we're going to go back and figure out what step 5 is now. So I hope I haven't confused you guys too much. I kind of a weird thing, but it is something that we're going to see incredibly regularly, right? So we're going to be dealing with voltage sources in circuits very regularly. And if we choose to employ this nodal analysis technique, then we need to get used to doing this, okay? So step 5 is what's going to allow us to come up with the correct number of equations, okay? And so what it is to write a voltage relationship equation for each voltage source. So let's look at that 2Vx voltage source or the supernode AB. Actually, let me do something crap. I'm just going to move this down and label this equation as KCL at supernode AB. All right. Sorry for being a little messy today, or messier than usual today. So we're going to start with a voltage relationship equation for the 2Vx voltage source. So we have 2Vx. How do you think, or does anybody have any intuition as to how we might write a voltage relationship equation for this? So how have we expressed voltages that aren't nodal voltages in the past? Whatever node is at the positive polarity terminal minus whatever nodal voltage is at the negative polarity terminal. That's the exact same thing we're going to do here. So what's the nodal voltage at the positive polarity terminal of the 2Vx source?
Be VA minus V.
Exactly right. VA minus VB. Okay. We have a second voltage source. So we're going to have another equation that's literally just going to be 5 volts. The voltage supplied by the source is equal to the voltage at the positive polarity terminal of the 5-volt source minus the voltage that's at the negative polarity terminal of the 5-volt source. So somebody tell me what that's going to look like.
VC minus 0.
Exactly right. So 5 volts is equal to VC. So it turns out that whenever we have particularly independent voltage sources, this actually makes our nodal analysis much easier because we are given some of our nodal voltages, right? So we don't have KCL relationships to worry about. We just have very simple voltage relationships that are going to take the place of some of those more complicated KCL relationships. So just for the sake of argument here, here's our first equation, second equation, third equation, fourth equation. How many total unknowns should we have?
Four total equations, 4 unknowns.
So I think we have 5 unknowns because we
5.
have those voltages VA, VB, VC, VD, but we also have that unknown quantity VX. So we really only need to come up with one more equation and then we're good to go. Well, that last equation is going to come from write a KCL equation for any remaining non-reference nodes, which in this case would literally just be KCL at node D. So what will our KCL equation at node D look like? That's just going to be this current plus this current.
VD over 4 ohms minus 3 amps.
Exactly right. VD over 4 ohms minus 3 amps is equal to 0. There's equation number 5. We could make a couple of simple substitutions here. So for example, everywhere that we see Vx, which would be, I think, just right here, we could replace that with VB. And everywhere we see VC, we could replace that with 5 volts, and we'd get this down into a 3 equation, 3 unknown system. I want to show you guys how to use MathCAD to solve systems of equations instead, because you definitely are going to have some homework problems where doing substitutions are only going to make the problem probably more complicated, okay? So if you look at homework set number 6, say problem 7, and Lord knows I understand that that problem is annoying. I believe you're going to wind up having a system of 11 equations and 11 unknowns, if memory serves me correctly. Doing that by hand would be an absolute nightmare. So I want to introduce you guys to computer algebra tools like MathCAD that will allow you to solve these systems with a little less effort. So let me open up MathCAD on my computer. Hopefully you guys all see what looks like kind of a sheet of graph paper. I guess that's not helpful because my engineering pad also kind of looks like graph paper. Did you guys see me switch to a different program?
You're on MathCAD
Yes,
for us.
sir, you're on
Okay,
math.
great, sorry. So as Louisiana Tech students, you all have access to MathCAD. If I'm remembering correctly, and I may not be, so I'll need to double check on Canvas really quickly. I think I put a link for you guys to be able to download MathCAD and all of that kind of stuff if you haven't already in the introduction section of our Canvas page. I'm just double checking that really quick. And this is being slow. Yes, so the bottommost link under the introduction section says MathCAD Prime 8.0 download. If you click on that, it gives you a link, and then I also give you the login and password for that link. And when you click on the link, it'll give you instructions on, what the port number is and how to access the university license and all of that kind of good stuff. All right, so in order for us to solve a system of equations, we are going to have to use what's called a solve block. And this is one of the few functions of MathCAD that are buried behind the paywall. So it's a good thing that we have a university license for this. And the process for setting up a solve block is fairly straightforward, but it's not particularly intuitive. So I'm going to walk you through what these different things mean. Okay? So this first part of a solve block is called guess values. This, for lack of a better way of describing things, is kind of like how you would declare a variable in a computer program. So we are going to have 5 different variables: VA, VB, VC, VD, and VX. We're going to have to declare all of those by assigning them a guess value. So I'm going to start by putting in V. If I press Control _, that gives me a subscript. And now I'm going to do A. You don't have to do the subscripts and all that kind of stuff if you don't want to, but I'm going to try to make it match what we've done previously as best I can. And this is a great place for MathCAD to be really confusing. There are 3 different types of equal signs. They all mean different things. So the first equal sign that we're going to be introduced to is by pressing Shift and colon. And so it brings up this colon equal sign operator. And I'm going to type in 1 volt. I'm going to do something very similarly for VB through VX here really quickly. So this particular equal sign is effectively saying assign the variable on the left-hand side of the equal sign the value that is on the right-hand side of the equal sign. So that's why I'm saying that the stage is effectively declaring variables. Okay. So now I'm going to be in the constraints section because I've declared all 5 of my variables. I'm going to start typing up here where my cursor is, and once it realizes that I'm putting in a constraint equation, it'll make that constraint bracket larger to take that into account. So the constraint section is where I type in the equations that we developed in our nodal analysis. So I'm going to have to refer back to some of these really quickly. So our first equation was simply that Vx is equal to Vb, okay? So I'm going to type in Vx. Here's our next equal sign. This is control equals, and it gives us this boldface equal sign is equal to Vb. So this bold-faced equal sign effectively says force whatever is on the left-hand side of this equal sign to be equal to whatever is on the right-hand side of this equal sign. So these are the constraints for our system that have to be enforced in order for our answer to be accurate. So there's our first equation, and notice the constraints thing jumped up there because once I put in that boldface equal sign, it recognizes now you're typing in constraint equations. And I'm going to go ahead and put in the rest. So I'm going to have 2Vx is control equal to VA minus VB. And then 5 volts control equal VC. So I've done my first 3 equations. Now I'm going to have my KCL at supernode equation. So let's see, VA minus VC over 10. You don't have to use units, but because I've started using units, I'm going to continue to use units. So I'm going to show you guys how to do an uppercase omega really quickly. So if we go into symbols, we can see that we have access to the Greek alphabet, which is fine and dandy, but I'm never going to actually use these things because it's a pain in the butt. They have keyboard shortcuts. So for omega, it's capital W and then control G. So I type capital W and then I press control G and it converts that to capital omega. Some of you may be thinking, well, why the hell does that give you capital omega? So let me explain that really quickly. Lowercase w, control G, gives you lowercase omega. So capital W, control G, gives us uppercase omega. If I do T, control G, that gives me the Greek letter tau. Capital T, control G gives me the Greek letter capital tau, which just looks like a big T. So anyway, that's the logic behind that. So you don't actually need to go up to that menu if you know how your Greek alphabet corresponds to the Roman alphabet. You can figure out 90% of these pretty easily. All right, so VA minus VC over 10 ohms plus VA over 8 ohms. Sorry, plus VB over 6 ohms. And then lastly, we have plus 3 amps. Equals 0. And then my last KCL equation was VD over 4 minus 3 amps. And I'm going to just scroll this down here. So I've put my 5 guess values in. I've typed in my 5 constraint equations. Now I need to make MathCAD solve. So the step that I'm about to do is technically optional. However, I strongly encourage you guys to do it every single time. What I'm going to do is I'm going to put in a matrix here. And if I have 5 variables, then I want a 5x1 matrix. And now I'm just going to type my variables in. So VA, then VB, then VC, then VD, and lastly VX. I'm going to shift equals, then type in the word find, open parentheses, and then type in those variables again. And now for the last equal sign, I will literally just type in the equal key with no control or shift or anything like that. And that's going to tell MathCAD to go ahead and give me what all those answers are. Okay. So the reason why I put that matrix in is that's, I guess, kind of MathCAD's way of declaring a global variable, if you will. So that allows me to access the nodal voltage VA outside of the solve block. If I didn't have this matrix in here, stop being dumb. It tells me that this variable is undefined. So in this particular class and in most circuit analysis classes, we're going to find our nodal voltages, and then we're going to use those nodal voltages to find other quantities like we did in the first problem. If I don't use that matrix there, I don't have access to those stored variables. So that's why I think it's important that you guys just get in the habit of doing that. So anyway, so that was using MathCAD to solve a system of equations. Happy to entertain any questions that you guys may have. And if you happen to be using MathCAD to solve a system for your homework or something like that, and it's giving you errors, you should take a screenshot of the error and then also send me your MathCAD file as well as the screenshot, and I can help walk you through what the error is, because MathCAD can be extremely finicky, and we'll be using it throughout the class, so I'll try to tell you about simple ways to avoid things. I know I've hit you guys with a whole bunch of information here today. We do still have 2 remaining in-class assignment problems to work, but can I answer any questions before we get on those? All right. So let's look at in-class assignment problem number 2. So for problem 2, this is our circuit of interest. Looking kind of similar to that first example problem I worked for you guys, but we're going to mess things up by adding in a voltage source. All right, so in this particular problem, we are asked to use nodal analysis and determine the power supplied by the dependent sources. Here on the right-hand side, I'm going to put P3V to question mark and P2Vx supplied is equal to question mark to remind us of what exactly it is that we're trying to do. Okay. So what's the first step for nodal analysis?
Pick the ground
Identify node.
or identify nodes,
Identify
yeah.
our nodes. Okay. So let's go ahead and do that. So I'm going to put a red node in the top left the blue node top right, the green node here in the middle, and an orange node on the bottom. What's our second step?
Assign ground.
All right, Baylor, because you told me the second step was assign ground, I'm going to let you choose ground.
The bottom middle.
So the bottom node.
Yeah.
So right here.
Yes, sir.
Okay. What's our next step?
Assign nodal voltages.
Assign our nodal voltages. Okay, so I'm going to do this as lazy as possible. So A, B, and C. What should our next step be?
Express Vx.
Okay, so express our controlling variable in terms of our nodal voltages. Absolutely right. So we're going to have Vx is equal to what? Somebody else tell me what's going on here.
So Vx would equal
Yep.
to VA minus VC.
VA minus VC. Great job. Okay. So what would our next step be?
Write a voltage relationship equation for each voltage source.
Exactly right. So we only have one voltage source. So that's going to look like 3Vx is equal to,
VB minus 0.
yep, so VB minus 0 is just VB. All right, what should our next step be?
Supernodes.
Okay, so specifically, we're supposed to write a Kirchhoff's current law equation for all supernodes that don't contain the reference. So I'm going to go ahead and circle my supernode. Everywhere I have a voltage source, I will have a supernode, just to remind you all. Since I only have one voltage source, I only have one supernode. Does this supernode contain the reference node?
Yes.
It does, because it's containing the ground, which means I don't write a KCL equation. I just move along to the next step. So what's the next step?
Write the
Just regular.
KCL equations for the rest of the non-reference nodes.
Sure, so let's start at node A. So somebody tell me what's going on for node A.
We would evaluate KCL number 2 going outward toward the 15 ohm to 3 ohm and one current source coming inward, which would be the 2 amps.
Yeah, so hit me with the equation.
It'll be VB minus VA divided by 3 ohms.
I
VC.
disagree. So if we're employing KCL at node A, it should be VA minus VB over 3. So we're adding together all of the currents that are leaving node A. So VA minus VB over 3 ohms. That's the current flowing to the right. Okay, what's next?
Minus
It'll
2
be-
amps.
Okay, what's next?
VA minus VC over 15 ohms. Or sorry, plus.
And that's equal to 0. Before we move along to the next KCL expression, are we all okay with all three terms here? I'm happy to explain why they are the way they are. Somebody had gotten cut off with other people answering over them, so I just want to make sure that we're all on the same page.
I had a question, Dr. Hart.
Go for it, Austin.
So on the, not the previous ICA, but on the, was it the previous ICA? No, on that example you did for the voltage and current series, we had two voltage sources, but one of them contained the ground. So by that sixth step, we would not have done one for that one as well.
Exactly right. So let me scroll back up here to that. So if we look at what we did, so we had our two voltage relationship equations, but we only did KCL at supernode AB. We did not do one for supernode C and ground. So because this supernode didn't contain the reference, it got a KCL equation. This supernode did contain the reference, so it did not get a KCL equation. So,
Yes, sir.
all right. Great question. All right, KCL at node C. Somebody tell me what that equation should look like.
You said at C?
Yes, please.
So at C, it'll be VC minus VA over 15 ohms.
Okay, so VC minus VA over 15 ohms. I agree with that.
Plus VC minus VB over 10 ohms.
So VC minus VB over 10 ohms. I agree with that.
Minus 2 VX.
Minus 2 Vx is equal to 0. And then we would solve these equations for VA, VB, VC, and Vx. Because we're running a little short on time, I'm going to leave you guys to solve the equations. Let's talk now about how we would determine these two powers that we are interested in. Let's start with the power supplied by the dependent current source, because that to me is a little bit easier. Okay. So for the dependent current source, we would need to know the voltage drop across this current source, which I'm going to call V2Vx, right? And I put the positive polarity on top and the negative polarity on bottom so that the current flows into the negative polarity terminal, so that that voltage times the current is just the supplied power. So how would I express that voltage V to Vx in terms of my nodal voltages?
Negative VC.
Why do you say it's negative VC?
Because, I'm sorry, that'd be incorrect. Be VC minus, it'd be positive VC.
Exactly right. So positive VC is the voltage. And then our current is just twice Vx. And we know that Vx is nothing more than VA minus VC. So throw numbers in that after we solve for our nodal voltages, and we have that power, okay? For our 3Vx source, this is one that's a little bit harder, okay? And the reason why it's harder is because we need to know the current flowing through a voltage source, which is rather difficult to express. So what we're going to do is we're going to use KCL here. So after we have done our nodal analysis and we know what our nodal voltages are, we could say, so let me start by saying, we're interested in finding the current that's flowing into the negative polarity terminal and out the positive polarity terminal. So I'm going to call this I 3Vx, like so. We could write it here, or we could write it here. It's the exact same current. And by using Kirchhoff's current law, we could say that I Vx is either this current flowing out plus this current flowing out, or it is this current flowing in plus this current flowing in. So that's just applying KCL at this node or applying KCL at this node. Do you guys have a particular preference?
B.
So at the bottom node?
I'd say VB.
Okay, so let's do that one. So our voltage is 3Vx, so that's just going to be 3 times VA minus VC. So what's the current flowing to the left through the 3 ohm resistor?
The VB minus VA over the 3 ohm.
So VB minus VA over 3 ohms, absolutely right. And what's the current flowing to the right through the 10 ohm resistor?
VB minus VC over 10 ohms.
Absolutely. So those are our two powers that we're interested in. So once we've performed our nodal analysis, then we can use those results to effectively apply or figure out the current that was flowing through that voltage source. And we could not have done that without having known those voltages first. Okay. So that's problem number 2. Before we move along to problem number 3, does anybody have any questions?
There's a third problem.
Oh, I thought there was a third problem, but I guess I expected this lecture to take longer, and so I only did 2. Okay. Well, do you want to solve this system and make sure that we're right, or do we feel relatively comfortable?
Would you mind showing us how to find the current in the 2Vx if we were to solve it from the bottom node?
Sure. So an alternative way to do this would be the same 3 VA minus VC, right? Because that's just the voltage. So what's this current right here in terms of that 2 amp current source, Baylor?
Just be the negative 2 amps as it's flowing in the opposite direction.
And so what's this current right here in terms of the 2Vx current source?
Be negative 2Vx.
Yeah, because it's flowing in the opposite direction. So negative 2 VA minus VC. That's it.
That's all right. I appreciate it.
No problem. Any other questions about this stuff or about any prior homework problems or anything like that?
I have a question on the most recent homework. I think it's question 3, part C.
Is this the superposition one?
I believe so.
Okay, let me pull it up really quickly. I will say, however, and maybe you guys saw this on the video where I rant about how terrible that homework set is, that I would argue using nodal analysis would be a better utilization of your time, because problem 3, B, and C is going to force you to set up a system of equations, even using superposition. And if we're going to use a system of equations, we should probably use nodal analysis, which we learned today, or mesh analysis, which we're learning on Friday. I will happily work this problem any way that you ask me to, but it's a pain in the butt using superposition for sure. So anyway, what would you like me to do? Just solve the whole thing, or you have any specific questions?
Just kind of the whole thing, because like I tried to do it the way with the kitchen sink method, and it wasn't clicking, and I was trying to put pieces together, and I just wasn't getting anything valuable out of it.
Draw this out really quickly. So we have a resistor here. For me, R2 is 64 ohms. Then I have a voltage source E2, where E2 is negative 17 ohms. So I'm going to choose to draw it positive polarity on the, excuse me, 17 volts, positive polarity on the right, just to get rid of that negative sign. I have a dependent current source here in the middle, so twice Vx. I have a resistance R1 that is 14 ohms for me, across which my voltage Vx is defined. And then I have a voltage source V1 here. V1 for me is negative, so once again, I'm going to just change the polarity in order to get rid of that negative sign.
So we can change the polarity to just get rid of negative signs if we need to.
Absolutely. That was something we learned on the second day of class. So changing the polarity on a voltage source is the same thing as multiplying the voltage source by a factor of -1. Changing the direction on a current source is the same thing as multiplying the current source by a factor of -1.
Okay, gotcha.
All right, so we're looking for Vx, it looks like. And you had suggested a kitchen sink. I'm happy to explore that if you want to. Look at something else.
Yeah, I'm fine. Kitchen sink is what I was thinking.
Okay. So let me think about things here. Okay, so let's call, just for the sake of argument, this voltage is going to be V64. This current is going to be I64. Let's make this current to be I14. Okay. So I'm going to write a KVL around the outside of the circuit or the perimeter. And so that would be negative V64 minus 17 volts plus Vx minus 30 volts is equal to 0. And I'm just going to rearrange that a little bit here. So I'm going to put Vx minus V60 is equal to 30 plus 17, so 47 volts. Any questions about my KVL equation?
So even though we have that current source in the middle, our voltage sources here are still in series.
They are not in series, but I can write a Kirchhoff's voltage law equation around any closed path. I just happen to choose the outside path, particularly because it avoids that current source where I don't know what the voltage drop across the current source is. So these are the easiest voltages for me to add together, which is why I chose that particular path.
Gotcha. I was just confused because I wasn't sure that we were even able to use like KVL unless we had voltage sources that were in series.
So we can use KVL in circuits where there aren't any voltage sources at all, as long as we are adding voltage drops around a closed path. So if we start and I started at this bottommost node and went clockwise around the outside of the circuit.
Gotcha. That makes a lot more sense.
All right, so now what I'm going to do is I'm going to do KCL at the top middle node. So to me, I have a current of 2Vx flowing in, so I'm just going to write that. And then I have a current of I64 and I14 flowing out. So that's going to look like I64 plus I14. I'm going to leave this one alone for right now. And now I'm going to use Ohm's law to express I64 in terms of V64 and I4. So what should I64 be in terms of V64?
Shouldn't it just be 17 divided by 64?
I disagree with that, because for there to be a 17-volt drop across the 64 ohm resistor, that would mean that the 64 ohm resistor would need to be in parallel with 17-volt source. They are connected at this node, but because this node and this node are not connected by a short, the 64 ohm resistor is not in parallel with a 17-volt source, which means we do not know that there's just a 17-volt drop across that. So what I'm going to do is I'm going to say that it is V64, some unknown voltage, divided by the 64 ohm resistor using Ohm's law. And very similarly, I'm going to say that I14 is just the voltage across the 14 ohm resistor, 14 ohms. I want to be really explicit here. Notice that both of the currents I defined are flowing into the positive polarity terminals of those respective voltages. So that's why these Ohm's law expressions have positive signs. So what I could do now is I could substitute both of these Ohm's law relationships into this equation up here, okay? So I'm going to have twice Vx minus Vx over 14 ohms. So let me just put 2 minus 1 over 14 ohms times Vx. So the 2 comes from here, and the 1/14 comes from this guy, and I move the I14 to the other side of the equal sign. And then I'm going to have minus 1 over 64 times and if you see now, I have two equations with two unknowns, which would allow me to solve for Vx. So that's how I would, quote unquote, kitchen sink this problem.
Thank you. I really appreciate it.
So if you will entertain my request here for a moment, let's do the same thing, but let's use nodal analysis. So the reason why I would prefer nodal analysis is because it's a more structured way to set up a system of equations, as opposed to just throwing whatever at it and hoping it sticks. Okay.
Mm-hmm.
So we have the exact same circuit. We'll just do all of the analysis down here below this line. So let's find our nodes, or identify our nodes would be a better way to put it. So there's 1, 3, and 4. Which node would you like to be our reference node?
Definitely the bottom side node.
So you're choosing this one down here as our reference. Okay, seems legit. So let's make this node A, B, and C. So how are we going to express our controlling variable Vx in terms of our nodal voltages?
Vx is going to be VB minus VC.
correct? All right, we have two voltage sources, so I need two voltage relationship equations. Let's start with a 17-volt source. So what's the nodal voltage at the positive polarity terminal of the 17-volt source?
It's VB.
Okay.
Right.
And what's the nodal voltage at the negative polarity terminal of the 17-volt source?
VA. So it'll be VB minus VA.
Yep. And so you tell me what's going on with the 30-volt source.
The 30-volt source is just going to be. Is that just going to be VC minus 0? So it's
Other way around. So the positive polarity terminal is at 0. The negative polarity terminal is at VC. So it should be 0 minus VC or negative VC. So whenever we're defining a voltage in terms of nodal voltages, it is always the nodal voltage at the positive polarity terminal minus the nodal voltage at the negative polarity terminal. All right, so our next step would be to write a KCL equation for all of our supernodes that do not contain our reference node. So I'm going to go ahead and identify those supernodes really quickly. So the supernode between EC and the ground obviously contains the reference node, so we're not going to write a KCL equation for that one. Instead, we're just going to have a KCL equation for a supernode AB. So that's going to be this current leaving plus this current leaving plus this current leaving. So tell me what those equations are going to be. So let's start with the current flowing down through the 64 ohm resistor.
that's going to be VA minus 0 divided by 64.
All right, so just VA over 64, okay. What about the current flowing down through the dependent source?
That's going to be. Is that just going to be negative 2Vx?
Exactly right. And the current flowing to the right through the 14 ohm resistor.
That's going to just be VB minus VC over 14 ohms.
Exactly correct. So we had four unknown quantities, VA, VB, VC, and VX. We have four equations, so now we would just solve this system. And realistically, everywhere we see VC, we could replace it with negative 30 volts. Everywhere we see VX, we could replace it with VB minus VA. So we could boil this down into a two equation, two unknown system like we have up here within another step or two of algebra. And we'd wind up getting the exact same results.
Awesome. Thank you, Dr. Hartman.
No problem. Anyone else have any questions before we call it for the day?
Would you mind scrolling up for me to our last problem we did? Make sure I got everything.
This one?
The last ICA problem.
Is this not the last ICA?
Is it
Or do you mean the previous ICA?
this one right here that we're on?
Okay. Sorry, let me make sure you can get that last equation down there.
All right, I think I got everything. Appreciate it.
You're very welcome. All right, if there are no other questions, I will see you guys on Friday to cover mesh analysis. Thank you for your time, and I'll see you then.